Most of the time, we're doing these kinds of processes either one-off simulations, which take huge amounts of computational power to try and simulate these systems, or you're doing it experimentally, which is again a huge overhead cost to be trying to do this experimentally, both to have
Mhm.
the resources in house to do it experimentally, the infrastructure and the knowledge base. You'd have to have your employees available to do this experimentally.
Hi, everyone. Welcome to the Sustainable Supply Chain Podcast. My name is Tom Raftery, and with me on the show today, I have my special guest, Erik. Erik, welcome to the podcast. Would you like to introduce yourself?
Yeah, absolutely. Thank you, Tom. It's a pleasure to be here. My name is Dr. Erik Garcell. I'm the Director of Quantum Enterprise Development for Classiq's operations, at least in the North America geography here. And Classiq, the company I represent, operates in the quantum computing software space. Classiq is spelled with a Q, so it's a Classiq. And we develop and offer a software development platform for quantum programming. We want to turn quantum programming from something that's esoteric and intimidating to a lot of people into something that's approachable and familiar for anybody with a computer science degree, and programmers of all backgrounds. And at Classiq, we're doing that because we believe that the democratization of quantum computing is what's going to enable this new technology space, right? There's so many applications that this new tech can help out with and apply to, but if it's not widely accessible, if it's only accessible to the few with enough skills and deep education background required, it's not going to do much societal use, right? It won't be widely utilized and it won't help out in the long term.
And you mentioned you're making a software development platform for quantum computing.
Mhm.
So, analogous, I suppose, to Visual Studio for classic computers, your product is similar, except it's for quantum as opposed to classic computers. Why? As in, I can't exactly go on Amazon and buy a quantum computer. There are not a lot of them around. So, where's the demand for your software platform coming from?
Yeah, and it's funny you say that. It's quite expensive to be buying a quantum computer and have one, sitting in your facility, right? That's millions of dollars to do at this. There are companies that'll sell it to you. But funny you say Amazon, you can actually go on their cloud, and the same way you would buy time to use a supercomputer, or some of their GPU assets on the AWS cloud system, you can do the exact same thing for quantum computers. You can buy some credits and use quantum computers on the cloud. And a lot of these vendors, these cloud vendors, have these quantum clouds, right? Microsoft has a quantum cloud, IBM has a quantum cloud, AWS has a quantum cloud. So you could, if you wanted to, right now, buy some credit and go and play around with it a little bit. So you're right, though, that it is a new technology
Mhm.
and that we're developing something that is more Visual Studio based, kind of, something that's a platform that looks familiar, feels familiar, and gets to be something that's useful in this way. Because the way most people are programming these systems is almost the equivalent of Boolean logic for classical computing.
Okay, so more drag and drop than actually hard coding, as it were. So, why do we care? As in, first of all, this is the Sustainable Supply Chain podcast, not
Mhm.
the quantum computing or the next greatest thing in technology podcast. Why do listeners to this podcast and why do I care about quantum computing?
Yeah, because it has so many wide applications, and especially in optimization, which is a huge part of both sustainability and supply chain.
Mhm.
Um, we talk about all this from a scientific standpoint because things are still very scientific and dealing with some of these systems. We're getting to be more commercial in the industry. At the end of the day, what people need to know is that this is a new computing resource. In the same way that, when GPUs came out, they didn't replace the CPU, right? It worked alongside CPUs to allow computers to do things that maybe they weren't able to do before or were just too slow on that CPU. These new quantum resources, we can just call them, QPUs, right? These quantum computers are new processing resources that will more efficiently run certain types of algorithms,
Mhm.
but we wouldn't be doing a podcast over a quantum computer, right? That would be terribly inefficient. It's not what that technology is for. You're better served on your classical resources, but it's going to enable us to do things, in real time, a little snippier, a little faster, or do things that we didn't think were possible with compute resources before. So there's lots of applications in the space, and Like I said, optimization is one of the bread and butter applications for quantum computing that we know definitively. We can do it mathematically on paper. A quantum resources, quantum computing will be able to solve optimization problems exponentially faster than classical compute resources. For the same number of resource, you're going to get an exponential speed up in your quantum processing.
Right. Obviously, I'm not going to be using it for things like, as you mentioned, making podcasts,
Yeah.
writing emails, not going to get an exponential increase in the speed of writing or sending an email. But you mentioned optimization problems. So go into that in a little more detail for me, for people listening to the show. What kind of optimization problems would it be possible to solve exponentially faster with the likes of a quantum computer?
Absolutely. So you can think about things like a traveling salesman problem is a classical mathematical problem where you have a delivery driver coming from their pickup spot where they have to load all the packages. They have to go to so many different facilities and back to their original home base. This is classically a very difficult problem for regular computers to solve, but one that quantum computers can solve quite easily and nimbly. And this kind of problem, right, from starting from one location, having to loop back to that same location, but meeting, five, eight, 100, 1,000, different places you have to go along the way. The more places it has to go, the more computationally intensive it becomes. Kind of the value of quantum computing starts showing up. But this problem is how your packages get delivered to your house, right? UPS, FedEx, they have to optimize this. This is how the drones at an Amazon facility move packages from one place to another without also colliding with each other. How do you optimize those routes? How do you do this faster, cut costs? How do you route through commercial channels globally, right? Through airplanes, through shipping routes. And should a shipping route get blocked, which happens from time to time, right? The Suez Canal will get blocked, the Panama Canal will get blocked, and all of a sudden, all of these supply chain corporations have to figure out how do you reroute all of your operations in as minimal amount of time as possible without incurring, tremendous additional costs.
Mhm.
These are the kinds of problems that quantum computers are going to be able to help solve. And this actually gets a little bit away from a pure what's called the traveling salesman problem and gets into, if you're looking at it from a mathematical standpoint, what's called the unit commitment problem. How do you solve this and minimize costs while still meeting the need you have at the end of the day? It's fascinating the number of applications you can apply this to. There's urban planning you can have also, right? How do you set up a city most efficiently? Or how do you set up charging stations for your electric vehicles in a city in a way that makes most sense, in a way that's distributed and meets the needs of the citizens in that city?
Okay. And when we hear the term quantum computer, we often think of something that's way out in the future. Where are we really at in terms of real world deployments? I mean, you mentioned there are some cloud ones available through some of the big
Mhm.
tech companies. But if I were to start writing a program now to run on a quantum computer, am I going to be at the very, as it's called, a bleeding edge? Is it going to be painfully expensive? Would I be better off waiting 3, 4 years until there's more quantum computers and the price comes down?
Yeah, great question, right? And it depends on what kind of corporation you are, the size of your corporation, and how much having kind of this first mover impact matters.
Hmm.
Right? There are quantum computers that are being sold today. There's quantum computers without going too deep into, the differences between all these systems. There's quantum computers sold by companies like D-Wave, IonQ, QEra, IQM. There's plenty of companies you can buy these systems from today, have them deployed in your system. There's even, third-party integrators that'll help you put all the pieces together for you, like a company called Trek that will take the hardware and the software and your infrastructure and make sure it all works, cohesively together. So we have the ecosystem and the model to put it together, but you would be on the bleeding edge if you wanted to start using it today,
Mhm.
right? You would be one of these, first movers to be utilizing this technology. But one of the things to consider too is how long will it take for your company to implement this technology, right? Because if you wanted to start using it today, you needed to have started this journey 3 years ago.
Okay.
You can't just turn around and say, I want to start using it. So starting investigating this technology won't be, you're not going to be putting it into your products tomorrow, or the advantages thereof. It's a bit of a digital transformation roadmap. It's going to be a bit of time to make sure that, this new compute resource works alongside your CPUs and GPUs, that it goes through all of your SOC 2 security, all right, that you're not breaking any MSA agreements with your clients if it's integrated into those kind of things or applying to them. There are very interesting applications happening. Unless you're a Fortune 1000 company, I wouldn't consider buying hardware today. I would consider using the resources on the cloud, and as they increase, you can just pay for the credits on the new systems as they come out, because the technology is moving very quickly. So for most users of this technology, I would definitely advocate use it on the cloud as they advance and evolve with the cloud as those new resources get advanced and move forward. So
Sure.
there's lots of different applications, and it depends on how many resources you need on that quantum system to do the thing you want to.
And how different are the different cloud provided quantum computers from one another? In other words, if I decide to go down the D Wave route or
Yeah.
the Ionic one or the Microsoft one or the Alibaba one or whatever, do I need to worry about vendor lock in? Do I need to, if I want to move from one to the other in 3 years' time, is all the work that I've done on one thrown out and I have to start again?
A little bit of column A and a little bit of column B on that answer. So I think it's first important to say that there are two types of quantum computers being developed.
Right.
There's a type of quantum computer being developed that's called a quantum annealer, and that's the kind of quantum computing system that is being produced by D-Wave. And there is the type of quantum computer called a gate-based or universal gate-based quantum computer that's being produced at first, kind of the likes of IBM and now many other companies. So we have these two types of programming and quantum systems being developed.
Okay. And coming back to supply chains,
Mhm.
given this is the Sustainable Supply Chain podcast,
Fair.
there's a lot of talk in the supply chain space recently around resilience. Do you see any way that quantum could help make supply chains more adaptable and robust in the event of shocks?
Absolutely. Yeah, one of the things that quantum computing, it's not going to be a near-term application for quantum computing, but this is
Mhm.
definitely one of them is real time adapting to scenarios. Solving these very, very large mathematical problems at the end of the day, these graph theory problems with many, many nodes and routes between them, your destinations and how long it's going to take or the costs incurred, hugely computationally intensive to figure out the best or most optimal path.
Mhm.
And as soon as one of those routes is disrupted, it disrupts the entire industry. It disrupts your entire system because it's not an easy task to recompute that. It's not a fast task. It's not a cheap task. And to get to an answer with any kind of confidence means that that algorithm probably has to chug for a long time to get to something with a high enough confidence interval, mathematically. So
Mhm.
quantum computing is going to speed that up by making that class of problem not as computationally intensive if you run it on a quantum computer, means that it's now something you can run in more of a real-time scenario. And as the hardware gets larger and larger, you're going to be able to more dynamically run these optimization algorithms time and time again. It might be that in a year you'll only be able to do it once a month. Then, in 6 months you'll be able to run it once a week. And you'll get to a point where the hardware is large enough, you have enough of these compute resources where you can have an on-demand recalculation of your optimizations. So it's going to make it more robust in this way, but also in the identification of almost new nodes on your graph, right? If you're talking about sustainability, right? If we look at energy grids, what you can do right now is identify a weak point in your energy grid, right? If this plant goes down, or if this one line between, my grid goes down, it disconnects the city into these two wholly separate parts that aren't talking to each other anymore. We can use quantum computing to identify more readily these vulnerabilities, right?
Okay.
Where is there a weak point in my energy grid infrastructure? How might I shore it up? And where would I put a new node, a new plant, a new generator, or new electrical lines to shore up these vulnerabilities?
And Classiq, you've worked with names like BMW and Rolls-Royce. What lessons have you taken from those kind of projects that could apply more broadly to supply chain sustainability?
We're finding that once you start looking at quantum computer as fundamentally as a new compute resource, once you start thinking about quantum computing as an engineer or a computer scientist would, that's what starts opening up the applications for what you can do with this technology and goes, okay, I get this now. I get the applications for it. We worked with BMW. They were a fabulous group. They already knew how to program in quantum computing. We had, I think, a 1 week intensive workshop with them to do something. They came to us with an academic paper and said, hey, we thought that this application that was talked about in a paper was really cool. How do we do that actually with a quantum computer? How do we do this hypothetical thing practically?
Mm.
And we showed them in our platform, how do you put that kind of algorithm together? How do you use it and how do you move forward? So we were solving that unit commitment problem we were talking about. They
Right.
wanted to look at cooling systems in their engines, right, in their cars. So if you have an engine, if you have these different parts, if you have a car battery all running, how do you cool these systems as efficiently as possible? Where do you put the cooling systems
Mm.
to make that optimized? And how do you do that with a quantum computer? How do you program that in? And once they start getting this, okay, now I get how to think about quantum computers and how to use it, how to put these algorithms together. Now BMW feels more confident to run and perform other projects that use these kinds of frameworks, right?
Right.
You can think about the problem as a problem, right? As the challenge you're facing at the forefront. So we worked with BMW in this way. We worked with Rolls-Royce's avionics division doing computational fluid dynamics and plenty of others, right? We talked about some already here. I know we worked with Mitsubishi Chemicals on some interesting chemistry applications.
Sure.
So it just uses less resources and it's easier to do than having a classical computer pretend to behave quantumly.
Okay.
Um, yeah.
So
Uh,
talking about chemistry, things like making higher energy density batteries for EVs and for utilities, for energy storage, or on the intro call, I mentioned the Haber-Bosch process, for example. These kind of things,
yep.
those would be ideal, I assume, for quantum computers.
Exactly. These are the kind of problems that quantum computers are going to unlock, right? These problems were very difficult to solve. These problems, for electric batteries, even for drug discovery and things like this.
Mm.
Most of the time, we're doing these kinds of processes either one-off simulations, which take huge amounts of computational power to try and simulate these systems, or you're doing it experimentally, which is again a huge overhead cost to be trying to do this experimentally, both to have
Mhm.
the resources in house to do it experimentally, the infrastructure and the knowledge base. You'd have to have your employees available to do this experimentally. So quantum computing is going to unlock the ability to do chemistry simulations, chemistry modeling computationally. It's going to make that much easier. So you're going to be able to use quantum computing to simulate what's the band gap if I put this chemical and this chemical together? How would that work out practically? What's the heat dissipation look like if I also put that together in an infrastructure, right? You start mixing in these problems. There's the chemistry side of it. There's, we're talking about heat dissipation. That's the computational fluid dynamics part of
Mhm.
things. Quantum computing is going to be able to put these pieces of the puzzle together to make it so that you can solve things like the Haber-Bosch problem or carbon capture. Also, how do we, what chemicals, what can we put together that would be able to both capture and store carbon for longer periods of time? What can we do that would enable that? You're going to be able to simulate systems that will be able to solve these problems. So whether you're trying to solve the Haber-Bosch or carbon capture, or I can't say definitively, but I know most are automotive manufacturers are looking at quantum computing already for building better batteries, both for having more storage, but also faster charging of these batteries. Because no client of their EV cars wants to wait 20 hours for that car to charge. You want to get to 80% charge within an hour. How do you get there? What will get
Um,
you there and storage
most
power?
most EVs can do it now. Most new EVs can go
Yep.
to 80% now in 30 minutes or less.
Exactly. These kinds of things are what's being investigated and can absolutely help out with. I've used some of them in my graduate career called like a ComSol or some of these other platforms you can use that do multi-physics simulations. But if you're doing a large system, you're only going to be able to either simulate a small part of your system with
Mhm.
a high granularity, or if you're simulating your whole system, you're going to have it be very low resolution to be able to do your whole system, with any confidence. So quantum computers is going to make it so that you can do your whole system with a higher granularity, with more confidence, or with, finer time steps.
Sure.
Because you don't want to find out in the air that your airplane vibrated at a certain frequency you weren't aware of when hit by a certain wind turbulence at a certain angle. That's a bad thing to find out. And
Sure.
you didn't figure it out because the grid sizes of your mesh on your simulation, right? The areas you're doing your physics on were too large to actually see that in the modeling.
Sure. Yeah.
These are the things that quantum computing is going to help out with and really help speed up and enable, right? So much of what quantum computing is going to help out with is almost going to feel like how AI has helped out in ways
Mhm.
where it's been in most every product we've used already, right? When you do a phone typing and you get all those, autocorrects on your phone, that was AI. I think quantum computing will probably evolve in the same way. It's going to be used in a lot of these background calculations. It's going to be used in ways that most everyday users of technology won't see or even realize quantum computing is being used or implemented until it hits a level of computational power and ease that anybody can go ahead and start doing some fun things with it.
Do businesses now need a whole new team of quantum scientists, or can they upskill existing people? If I'm a manager now, I'm saying to myself, "This sounds cool, but I don't have a quantum PhD in staff. Where do I even begin?"
Yeah, that's a great question actually, because every quantum conference I go to, there's at least one panel talk or one topic or session on the quantum talent shortage. Right? The need for those skilled in this industry is growing faster than those skilled in this industry. People gaining these skills. So while universities are spooling up their programs to train students on how to program and use this new technology, right? You see tons of these new university offerings popping up on quantum education and quantum software development, but this need is booming in such a way that managers are having to figure out right now, should I pay for one of these, frankly, very expensive new graduates
Mhm.
with this skill set, or can I upskill my existing team?
Mhm.
And there's advantages there too, because your existing team knows your infrastructure very well. They know the problems you're trying to solve. They know your clients and what's needed and how the rest of your system works together. So it would be highly advantageous for these managers to upskill their current employees. If you're using a platform like Classiq or any of our competitors that are trying to move quantum computing to this higher abstracted level, right? To something that's more analogous to classical computing, it's much easier to upskill your current engineers. It becomes a much cheaper prospect, a much more feasible prospect because it takes frankly less training time, right? It's not as big a lift to train somebody to program C++ than it would in pure Boolean logic,
Mhm.
right? It's just a less heavy lift. It's going to cost less. It's going to take less time, and it's easier for a manager to say yes to upskilling those current engineers. So it depends on what you're trying to do in quantum computing. I think you do need somebody who understands where quantum computing will help your infrastructure and help your
Sure.
company.
Mhm.
Where it won't is equally as important to understand from the starting point. So you can do that in a couple of different ways. You can hire somebody to help you out with this, one of these students who are educated in this. You could work with a number of companies that will facilitate that investigation, that help, that work on figuring out where in your corporation might quantum computing assist with, where won't it help with, what are the timelines we're looking at for this. For most of the development thereof, we're getting to a place where you can upskill your current workforce. You can take your current software developers, take a day a week for them to do some training on this new way of programming and how to connect that to their classical resources. We're working already in a place where quantum computing and classical computing are connecting. They're not disparate systems, but in this way, your engineers are probably going to be more sophisticated in your current HPC stack than somebody new you hire. While somebody new would have the expertise and the know-how of quantum computing, you still need your your in-house software developers to learn these skills, to upskill and help that newcomer figure out how do you connect all the cool things you're doing with our HPC stack. I still think you need somebody who can help you kind of understands the ins and out, but at this point we're getting to a place where most managers can and should upskill their current workforce.
And if you put on your futurist hat, what's the moonshot potential of quantum computing for supply chain sustainability over the next decade?
If I could have my magic wand and say what would be the really cool application for this for logistics and supply chain, I think it would be real time dynamic logistic calculations. I think it would be phenomenal to say there's a road outage that just happened. There's inclement weather that's impacting certain routes, or for safety reasons, it's not good to go that way. Quantum computing tied into essentially many different data repositories, being able to chug all that big data, analytical data on weather, on road traffic, on real time costs incurred
Mm,
about one versus another traffic route or vendor that you're buying from, and having it be a dynamic real time calculation to both save in the time and cost incurred in any logistics operation. I think that would be kind of the end point, the really cool place to get with quantum computing, and where I can see it bringing a lot of good to logistics.
sure. And
Yeah,
optimizing for reduced carbon as well, obviously.
absolutely. Yeah. So thank you for that, right? The one route's going to be shorter. So, I mean, it depends on what your company's most interested in, right? And
Mm,
having that be part of that calculation, right? There's the cost incurred, but there's also carbon, right?
mm.
Even in Google Maps today, you can choose, do I want the shortest distance? Do I want the fastest distance? And I think now they have a little button that says, right, this is the eco-friendly route.
Okay, good.
We're going to have that too with logistics. You know, how important is the cost savings versus the carbon emission of this route versus that route, or sending certain parts of your fleet of trucks.
Mm.
Should I send the EV trucks? Should I send the gas trucks? Maybe you have some gas trucks on reserve for certain situations. When should I deploy them? These are the kinds of things that I can definitely see quantum computing helping out with, having a big impact, and ultimately optimizing these so we have lower costs, lower emissions, faster times to delivery, faster times to accomplishing your goals, whatever they may be.
There's been a lot of talk as well about quantum breaking encryption. Should supply chain leaders be losing sleep over this?
This is one where I think that is the application that's getting definitely the government's attention, right? RSA being broken is a big deal and a big deal for a lot of companies, right? RSA encryption is how we encrypt most of the data on every computer you're using, right? Your laptops are using RSA encryption for how it communicates to other computers, how you're doing most everything. It is true that quantum computers are going to break RSA encryption. It's not
Mm,
an if, it's a when statement. One of the big cloud vendors finished putting a publication saying, "Hey, we just came out with a an optimal way to program what's called Shor's algorithm, which does RSA encryption, which actually just sped up the timeline for when RSA will be broken by quantum computers." So it is something you have to worry about with caveats. Any
mm,
company now has to look and say, how long does my company's data matter for? Will my data that I have and store today securely have any value to my corporation or cause any legal issues if it got out in 5 and 10 years? If the answer is in 5 years, the data I'm storing today has no value, you don't need to worry. You're good. Corporations and government institutions, like in the US where I'm at, NIST, the National Institute for Standards and Technology, has already been investigating quantum computing safe security protocols, figuring out which are the most robust, easiest to implement, and coming up with new standards for what to transition into and how to do that transition.
mm.
And once they come up with their standard, third party integrators are going to come out and help you with that transition once it's standardized. So if your data doesn't matter for more than 5 years, if it's not going to bring you value more than 5 years, wait for your government to come out with new standards, wait for those third parties to come out, and they will, you can pay for their service, they'll help you migrate. Do migrate when that happens, absolutely, or your data will be available to be decrypted. I wouldn't say you have to worry anytime soon for that. Now, if your data does have value in the next 5, 10 years, if you're a government contractor, if you are a government entity, right, your data matters. And what bad actors are doing right now, I would say, is what's called take now, decrypt later. They're taking data, storing it, even if it's encrypted, they can't break into it right now. When computers get powerful enough in 5 or 10 years to do this, then they'll be able to break into it and see the data that they collected 5 years ago. So if that data still has value, then you're in trouble. Because now you can consider anything that you have that is of high value almost as if it's already been broken into, right? So you do have a bit of a lead on that. So as long as you shore up your systems now, most people are good. But we are in a hairy place where if you have high value data, it may have already been gathered, and in
Mm.
5 or 10 years, it's probably going to be public or used by a bad actor in some way. So that's why governments are so worried about it. As a corporation, for this quantum breaking RSA encryption, how long does your data matter for? If it matters and brings you value or creates some kind of security issue for you in 5 or 10 years, you do have to worry if it brings you that value. If your data doesn't matter at all in 5 years, who cares who sees it in 5 years? You should be holding on to it and keeping it secure, but it's not going to cause any issues, any regulatory, any cost incurred to your corporation within the next 5 years. You're fine. Move over when your country says to move over. Move over when these third parties are there and available to help you migrate your current RSA to further protocols.
Okay, fair enough. Left field question for you.
All right. Oh, I like these.
If you could have any person or character,
Yeah.
alive or dead, real or fictional, as a champion for quantum computing in supply chain, who would it be and why?
Oh my. A champion. Ooh. I've always been quite the fan of Richard Feynman. There's a couple of physicists out there in the world who over time have shown to have the knowledge to understand the intense mathematics and concepts going on, but the kind of broad overview of many industries and the capacity to tie these things together in
Mm.
new and interesting ways. I think Richard Feynman was a physicist who was able to do that. He worked on the Manhattan Project, and he was one of the first advocates and kind of proponents for quantum computing. I think very famously, I'll say an abridged, clean version of it because I think he gets a bit colorful in the quote too. He said, what the world behaves quantum mechanically, right? Nature behaves quantum mechanically. So if you want to simulate nature, you need to use a quantum computer, right? It seemed almost simple for him, right? If you want to simulate this thing that happens in a certain way, you need to simulate it in a certain way. And he always believed that this would be something that would be possible. It was an inevitability. And I would love to see his thoughts on this new technology and where it can apply and how it can apply. He had the mind to be able to see kind of logical consequences of these new technologies, of these new calculations, how it can apply, and how it can apply to so many different industries and cross-disciplinary fields. Because he was also a physicist who got away from physics every once in a while and started publishing in chemistry and doing really interesting things in different fields, but saw all the ties and how they really all do connect together at the end of the day from its core principles. So it would be really fun to have a chat with Richard Feynman and say, where do you see this going and how do you see this connecting to all these different industries and applications, the problems we have in the world, and given this technology and new compute resources, what would you do with it? I would love
Mm.
to hear his answer on that.
Great. We're coming towards the end of the podcast now, Eric. Is there any question I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
Yeah, I think one of the biggest things we deal with as far as being individuals in the quantum computing industry is a notion that quantum computing is this Herculean thing, right? This mountain of intimidation. I talk to companies, and as soon as I say the word quantum, it brings up notions of physics. Something about physics has a connotation of being extremely difficult. If you're doing it, oh, you must be a smart person. It almost has this concept of difficulty. So we get a not it situation where on the call everyone puts their fingers to the nose and says, "Ooh, not it." You know, I'll let somebody else in my company handle the quantum side. But we're getting to a place where quantum computing is becoming more intimidating than it should be seen as. It is more computer science than physics. You can do interesting problems and solve interesting challenges using this new technology. While it still has a stigma of being difficult, it's not as intimidating as you're probably imagining it to be. You can go online right now and program a problem that does a raffle for a contestant of, at a convention, or, you put your business card in a fishbowl and pick out who the winner is using a quantum computer. You can put together GUI applications with quantum computing. You can do interesting problems that at the end of the day will look the same as any other classical computing thing you've done, right? You can put these kinds of interesting programs together using this new resource and have fun exploring it, right? Quantum computing is no longer as intimidating as people might imagine it to be. It's a new resource that companies should be investigating because it will apply to almost every industry. It's just a matter of where will it apply for you and when will it apply for you are the questions that each company and corporation needs to find out the answers for themselves on.
Erik, if people would like to know more about yourself or
Mhm.
any of the things we discussed on the podcast today, where would you have me direct them?
Absolutely. Feel free to visit our website, classiq.io. So classiq.io. We have lots of resources there. If you're looking at quantum code, there's a link to our GitHub that you can have some fun and check out different use cases and applications. And feel free to reach out to me directly also. I'm always happy to talk about quantum computing like this, Tom. I have a blast answering these questions, and I love helping people figure out how quantum can apply, where it can apply, and all the fun that you can have with it. So feel free to email me at Erik, Erik, at classiq.io.
Brilliant. Super. Erik, that's been fascinating. Thanks a million for coming on the podcast today.
Thank you for having me, Tom.